Good morning, students. Today's lesson is magnetic effect of current. This is lesson 1 of the chapter number 4. Magnetic field strength refers to a physical quantity that is used as one of the basic measures of the intensity of the magnetic field. The unit of magnetic field strength happens to be ampere per meter. Furthermore, the symbol of the magnetic field strength is H. It is independent of the medium surrounding. The electric current produces the around, and it is also produced by the magnet when we are not considering the surrounding medium. There is another quantity that is called B. B is different than H only regarding the medium around. B is also known as magnetic induction or magnetic field strength. The magnetic field strength depends on the medium around. B and H are proportional to each other with the multiplicative constant depending on the physical constant. This is a physical unit. Inside material, they are B, whereas when in vacuum, if we can write B, we will be writing B as is equal to mu naught into H. Mu naught is the characteristic of the medium. Let us begin with an experiment where we are going to draw the magnetic field lines. There are two things. There is a compass needle, you can see, and there is a magnetic field meter. At first, we are going to trace some of the magnetic field lines. You can see the North Pole is represented by red, and compass needle also has red. They are actually repelling each field line, and you can see they are starting from North Pole and ending at South Pole. But once it is inside, I have shown the inside also. Once inside, they are from South to North Pole. Now let us find something else. We can find out the magnetic field intensity B, that is the magnetic induction, and its Bx and By. So they are measured in Gauss. Gauss is equal to 10 to the power minus 4 Tesla. Tesla is the magnetic. Tesla is the SI unit of the magnetic field intensity. Now see, we can have at certain distance we are having the magnetic field strength B is equal to 1 Gauss. The Bx is equal to 0.66 and By is equal to 0.74. Can go nearer, you can see the magnetic field strengths are increasing. It is found to decrease with 1 by r square. So B is inversely proportional to r square. You can see in the either direction it is in 3D. You can have these values. There is a minus and a plus sign. Minus sign is when the Bx is along negative x-axis and plus is along positive. By is negative here, you can see. That means it is along negative y. So magnetic effect of current, let me tell you about magnetic field once again. Magnetic field can be defined in two ways. One crude method is there, though it's only for the theoretical concept. That is, it is the magnetic field intensity is the force experienced by a unit strength magnetic North Pole placed at certain point inside a magnetic field. But as there is no unit North Pole present anywhere, it's not practically possible. So it can be shown by another means. It can be given by the force experienced by a unit positive test charge moving perpendicular through a point with an unit velocity. So this concept has come from the concept of Lorentz force. I will talk about Lorentz force in my subsequent lessons. So what is the point there? In electric current, that is the flow of electric charge, produce magnetic effect in the space around the conductor called strength of magnetic field or simply magnetic field. There is an experiment. It's an Oersted experiment. In fact, it was accidentally invented, but this is the basic idea which actually has given rise to the relation between electric current and the magnetic field. So this is a circuit. In the circuit there is a key and a battery E, and there is a rheostat. So with the help of the rheostat you can change the current. Now if you place one compass needle, remember the compass needle's north pole is red in color. Now if I switch on the circuit, current flows, the compass needle will rotate. The rotation of the compass needle can be found out by many methods. One of them is known as Ampere's swimming rule, but I will talk about it a bit later. When current was allowed to flow through a wire placed parallel to the axis of a magnetic needle kept directly below the wire, the needle was found to deflect from the normal position. So the needle deflects. In fact, it was accidentally found, as I told you, due to the presence of a squirrel inside the laboratory of Oersted, and he actually discussed it with his students. So two students, they have taken it as a project. Their name is Bayot and Severt. I'll talk about that also. Now if the electric current reverses, now what you see, the current reversing, the north pole is deflected in the other direction. When current was reversed through the wire, the needle was found to deflect in the opposite direction to the earlier case. Now I can show you the rules. This one rule I have shown here is the corkscrew rule. This is Maxwell's corkscrew rule. I will talk about that, but the main one is the Ampere's swimming rule. So what is Ampere's swimming rule? This is also called snow rule. In this case, imagine a man who swims in the direction of current from south to north facing magnetic needle kept under him such that the current enters his feet in the north pole of the needle will deflect towards his left hand. Yes, now can you see? It will be deflecting towards his left hand. So this is one very famous original rule, but later on it has been modified by Maxwell's corkscrew rule or right hand thumb rule or right hand screw rule. If forward motion of an imaginary right-handed screw is in the direction of the current through a linear conductor, then the direction of rotation of the screw gives the direction of magnetic field of force around the current. Actually, magnetic lines of induction they are called. I have shown you two right-handed and left-handed screws there. Right-hand thumb rule or curl rule. What does it say? If current is along the direction of thumb, the magnetic field direction B is along the curled fingers of the right hand. Okay, if a current carrying conductor is imagined to be held in the right hand such that the thumb point in the direction of current, then the tips of the finger encircling the conductor will give you the direction of the magnetic lines of force or lines of induction. Bayot-Severt's law. I just mentioned Bayot and Severt. They were two students of Oersted who has experimentally found different types of conductor. For different types of conductor, they have found out Bayot and Severt are two different people. They found out the magnetic field at a particular point. So the point P, the magnetic field, this is due to a small element dl. dl is a small element where the current is almost constant and along the direction of the conductor. So this is one concept. So I into dl is also known as current element, and this is equivalent to q into v. Q is the charge and v is the velocity. Now at the point P, you can find out the direction of the magnetic field. R is the position vector of the point P. Theta is the angle made by it. There is another point P dash in the other side, and P dash also P has a magnetic field that is going inward. Put your finger along the I across DL, and you can find that the thumb will be going inside. Cross means inside and dot means coming out. So the strength of the magnetic field dV due to a small current element dl carrying a current I at a point distant r from the current directly proportional to I, dl and sine theta, and inversely proportional to the square of the distance r square, where theta is the angle between dl and r. Number 1, so the points I give in a mathematical way. dV is directly proportional to I, dV is directly proportional to dl, dV is directly proportional to sine theta, and dV is inversely proportional to r square. So dV will be directly proportional to I dl sine theta by r square. That constant of the constant of variation is mu naught by 4 pi, whose numerical value in a SI unit system is 10 to the power minus 7. Biot-Savart's law in vector form. The Biot-Savart's law can be formed in a vector way also, because dV is a vector quantity. So it will be mu naught by 4 pi, and it will be ideal is a vector cross r. Ideal is known as current element, already I told you, divided by r square. Now r cap can be also, r cap is the unit vector along the r, so this can be also written as vector r by its modulus. So it will be mu naught by 4 pi ideal cross r vector divided by r cube, where the value of mu naught is 4 pi into 10 to the power minus 7 Tesla meter per ampere or Weber per ampere meter. Direction of dB is same as the direction of dl cross r, which can be determined by the right hand screw rule. Do you remember right hand screw rule? Once again I tell you, right hand screw rule is when you are finding out dl cross r, so from dl to r, when your right hand curl fingers curl, then the thumb will point towards dl cross r. Current element is a vector quantity whose magnitude is the vector product of current and the length of small element having the direction of the flow of current ideal. Magnetic field due to a straight wire carrying current. So if there is a straight wire, this dl vector I have taken, this r is the position vector of the point P where we are going to find out the magnetic field. Then A is the perpendicular distance. Theta can be found there. A will make a 90 degree and R will make theta. Now by right hand thumb rule you can see I, if it is going upward, then the magnetic field intensity will be going inward into the plane of the paper. So this will be phi would be definitely equal to 90 minus theta. Then phi 1 is the lower limit and phi 2 is the upper limit for the entire length of the straight wire. B is the magnetic field intensity that is going inward. According to Biot-Savart's law, dB is equal to mu naught by 4 pi ideal sine theta by r square. Sine theta is equal to a by r. Then we can write this one is sine theta is equal to cos phi, because theta is equal to 90 minus phi. So sine theta is equal to sine 90 minus phi is equal to cos phi. So r is equal to a by cos phi. Tan phi is equal to very simple. Tan phi is equal to L by A. Now AL is equal to A sine phi, so DL is equal to A sec square phi into d phi. Substituting R and DL in dV, you'll get dV is equal to mu naught by 4 pi I cos phi d phi by A. Magnetic field due to whole conductor is obtained by integrating with limits minus phi 1 to plus phi 2. Minus phi 1 because it is below the axis, and plus phi because phi 2 is because it is in the above the positive axis. So B would be equal to integration of dB, and this is equal to minus phi 1 to phi 2 mu naught I cos phi d phi 4 pi by A. So that would be the formula mu naught I by 4 pi A sin phi 1 plus sin phi 2. Basically this relation you need not remember how to deduce it, but you should remember the answer for doing the numericals. A straight wire is infinitely long, then phi 1 and phi 2 would be pi by 2. Then B would be equal to mu naught 2I by 4 pi A or mu naught I by 2 pi A. Direction of B is same as that of the direction of DL cross R, which can be determined by right hand screw rule. It is perpendicular to the plane of the diagram and entering into the plane at P. So let us see the shape of the graph between B and A. So you can understand A is the perpendicular distance between the point and the conductor. So it is an infinitely long conductor, so it's a hyperbolic function. Magnetic field lines, let's see how the magnetic field lines, I, the right hand thumb towards the I, then the direction of the magnetic field lines are like this. This you can see in your experiment I have performed at the beginning of this lesson. You can see I towards your thumb, right hand thumb, and the direction of magnetic field are like this along the curved fingers. Magnetic field due to a circular loop carrying current at a point on the axial line. That's an important topic. Those two red color arcs are DL, small element. I is in the anti-clockwise direction. P is the point where we want to find out the magnetic field. OP is equal to X. R is the distance between the ideal at the top and the point P. This angle got to be 90 degree. Ideal at XY at point C. Similarly, we can have the dB would be the magnetic field due to ideal at point P. Very simple application of your right hand thumb rule, you can find out dB is perpendicular to R. So dB can be resolved into two components, dV cos phi and dV sin phi. dV cos phi is perpendicular to the line joining, and dV sin phi is along the line joining. And again at point D we have taken x dash y dash is the ideal. So dV once again can be found out. The reason dB cos phi are equal and opposite for two diametrically opposite ideals, the elements, so they will be cancelling out each other and dV sin phi will add up. So the net value you can find out by integrating dV sin phi. The plane coil is considered perpendicular to the plane of the diagram such that the direction of magnetic field can be visualized on the plane of the diagram. At C and D, current elements xy and x dash y dash are considered such that the current at C emerges out and D enters into the plane of the diagram. So you can get dV in either cases of element C and element D. dV is equal to mu naught by 4 pi ideal sin theta by r square, or dV is equal to mu naught ideal by 4 pi r square. Angle theta between DL and R is 90 degree because the radius of the loop is very small, and since sin 90 degree equal to 1. Then semi-vertical angle made by R to the loop is phi, and the angle between R and dV is equal to 90 degree. Therefore, the angle between vertical axis and dV is also phi. dV is resolved into component dV cos phi and dV sin phi due to diametrically opposite current elements. Cos phi component are always opposite, of course equal to each other, and hence they cancel out each other. Sin phi component due to all current elements dl get added up along the same direction in the direction away from the loop in this case. Of course, if it is clockwise current, then it will be towards the loop. Now this also depends on the point of viewing. So B is equal to integration of dV sin phi, integration of mu naught I dl sin phi by 4 pi r square, but there should be a limit. I tell you the limit after some time. So by integrating you get mu naught I 2 pi a divided by 4 pi a square plus x square into a square plus x square to the power half. This a by a square plus x square to the power half is the sin phi, value of sin phi. Now I was talking about the limit. Here the limit is actually the entire loop, the length of the loop. That means 2 pi a. 2 pi a is the length of the entire loop. That's the perimeter. So when you integrate it over the entire loop, it would be the integration of dl would be 2 pi a. So B is equal to mu naught I a square 2 a square plus a square to the power 3 by 2. So we got mu naught I a sin phi are constants. Integration of dl is equal to 2 pi a, and r and sin phi are replaced with measurable constant values. Now some special cases. Now in case the point is at the center of the circular coil, so B is equal to mu naught I. In that case x equal to 0, so B is equal to mu naught I by twice a. A is the radius of the coil. If there are n number of turns, then mu naught ni by twice a. If the observation point is very far away, that is a is very much greater than very much less than x, radius is very much less than the distance, so a square can be neglected in comparison to x square, and in that case B would equal to mu naught I a square by twice x cube. So the diagram on the graph will be like this. So B will be maximum at the center of the coil, and its value is B is equal to mu naught ni by twice a. Different views of direction of current and magnetic field due to circular loop of a coil, which here. So this is a circular loop passing through a cardboard. So that would be the magnetic field. At first it is circular, and then later on it is going in. Here another interesting result you can see. This time, if the current is towards the curled fingers of the right hand, then the thumb will point towards the magnetic field. Okay. At the center of the loop, the magnetic field is already it has been done. Going inward by pointing thumb, you can say the plane of the coil is lying in the plane of the diagram, and the direction of current is clockwise, such that the direction of current is clockwise, such that the direction of magnetic field is perpendicular into the plane. dV is equal to mu naught by 4 pi I dl sin theta by a square. So dV is equal to mu naught I dl by 4 pi a square. The angle theta between dl and a is 90 degree because the radius of the loop is very small, and since sin 90 degree equal to 1. So by integrating you get mu naught I by twice a. So mu naught ni by twice a also can be written if there are n number of turns there. The shape of the graph between B and A will be rectangular hyperbola. Magnetic field due to a solenoid. This is another experiment I will be doing just after these, a virtual experiment of course. So it's a solenoid. Solenoid is a pipe on which current is shown like this. This current is going like this. The first one is going in, and this last one, the bold one, is coming out. the current I is going like this, so you can see current is going like this and going in. At the top it is coming out, and at the bottom it is going in. So you can see the current is coming out. Now there will be a magnetic field produced due to this. The shape of the magnetic field would be like this. So that's about the magnetic field due to a solenoid. Remember, for a solenoid where the current is anti-clockwise, look at the diagram N there. So anti-clockwise current behaves as a north pole and magnetic field lines come out of it, and south pole it is clockwise where the magnetic field will appear as the south pole. So it will go in, the magnetic field will go in, and that will act as the south pole. Okay, when we look at the end of the coil carrying current, if the current is in anti-clockwise direction, the end of the coil behaves like north pole, and if the current is in the clockwise direction, then that end of the coil behaves as the south pole. Now let us do the virtual experiment I was talking about. Well, now we are showing the electromagnets. You can see there is a battery connected to a solenoid of 4 turns, and here the battery is given plus 10 volt, and once you start, you can see that when the current is flowing, we can have the magnetic field lines exactly like a bar magnet. You can put it at different place. The compass needle will trace the magnetic field lines, so it is exactly the same as that in the case of a bar magnet. Let us check some other things. You can see this is the tracing. Let us also check if we inverse the direction of the current. Now, so reversing the direction of current, you can see they are in the opposite direction. You can watch in either direction the magnetic field lines change their direction. So this certainly has got something to do with the direction of current. So the magnetic field lines, they depend on the direction of current. Now let us find out the magnetic field strength B. There are some other factors changing here, but we will be concentrating only on the V vector. The B is the magnetic induction. At certain distance, say its value is 3.94, 4.19, 5.15. So once we are getting nearer, the magnetic field strength are increasing. So it's 10.03, it's almost 10. Now let us increase the value of the current by increasing the battery first. You can see when the battery strength has been increased, the current increases, the magnetic field B also increases. Now let us decrease the number of turns. You can see the number of turns as decreases, the magnetic field strength also decreases proportionately at the same position. And this also changes with distance. Say at 1 centimeter its value is 43.04 Gauss. At 2 centimeter it is abruptly changing to 5.40. Here you can see By is minus but Bx is plus. But once you are going below, here the plus and minus is showing only the direction. Okay, in that way you can trace the magnetic field strength in the either direction. One last thing I want to show you. Say it is magnetic field strength is 1.62. I change the DC circuit into an AC circuit. Very interestingly, if the AC current supply is made stronger, the magnetic field strength as well as the compass needle, they're changing the direction. So along with the magnitude, you can understand that the direction also has got certain effect on it. So we'll be understanding this mathematically now. So let us stop.